Okay, so my junior venture project was on PneumoStack, my proposed approach to automated pneumonia diagnosis with deep transfer ensemble learning via convolutional neural networks and stack generalization. Okay, so I chose pneumonia as the disease of focus because pneumonia is the single largest infectious cause of death in children worldwide, accounting for 15% of all deaths of children under 5 years old. The principal tool of diagnosing the bacterial and viral pneumonia is the chest X-ray, as they can show airspace, opacity, lobar consolidation, or interstitial opacities that are characteristic to pneumonia. And for my project, I decided to focus on automating diagnosis methods with deep learning. Automated diagnosis can bring diagnostic tools to regions where pneumonia is most prevalent, South Asia and sub-Saharan Africa, for example, where trained radiologists are limited, leading to more accurate and widespread pneumonia diagnosis and treatment. The need for automation is also present today with the difficulty of differentiating between COVID-19 and non-COVID-19 viral pneumonia. In a recent study, the accuracy of 2 radiologists from China in differentiating between COVID-19 from non-COVID-19 viral pneumonia was 80% and 60%. On another note, recent reports have revealed that RT-PCR, that nose swab you get when you're testing for COVID, has a sensitivity as low as 60 to 71% for helping detect COVID-19, which presents the possibility for CXR analysis or chest X-ray analysis to validate or rectify findings in RT-PCR in COVID-19 diagnosis. Applied deep learning research has been limited to the proposal applied deep learning research has been limited to the proposal of existing transfer learning models. The highest performing models in these studies have frequently been transfer learning convolutional neural networks, or CNNs. There are a few studies that proposed an ensemble, but these ensembles were constructed by means such as bootstrap aggregation and voting methods, such as hard, soft, and weighted voting. Stack generalization has also been used in ensembles, though the base learners used are the same algorithm, which are then stacked together. The meta learner built is also an algorithm other than a neural network. So in contrast to other ensemble methods and the use of individual transfer learning models, the aim of this study is to present a stacked CNN meta learner of transfer learning CNNs with stack generalization in effort to achieve higher performance than any one of its constituent classifiers, meaning any one of the ensemble's base learners and existing individual models in binary and 3-category classification. Deep learning models were constructed, trained, and evaluated on Google Colab or Google Collaboratory with the specs as listed. And my mentor, Dr. Ying-Quinn Taylor, also helped me through debugging at the tertiary classification step and helped me take this project into new directions. Okay, so here's our procedure. First, I selected and pre-processed my data. I used the sklearn library to split the data into training and testing data. And also, I split the data into classes, which are pneumonia, COVID-19, and normal. I also augmented the data, meaning that I expanded the data set with a series of transformations shown here in figure 6. So in figure 6, I put together 9 images with horizontal flip, clockwise rotation by 15 degrees, vertical shift by 10%, and horizontal shift by 10%. And these are the data augmentation transformations used in this study. The reason for data augmentation is that more training data is beneficial because the model can learn to tell which scan belongs to which class, even if the scan is shifted a little to the right or is upside down. And more data can also lead to lower estimation variance and hence better predictive performance. And then I constructed the individual transfer learning models, Exception, Resonant 50, and Inception Resonant version 2 with Keras. another Python library, and fine-tune the models with the layer freezing procedure, which I'll go into more later. So I just froze the first 10 layers of the, sorry, that's my dog. I just froze the first 10 layers of the model to accelerate meta-learn or ensemble learning or training. And after compiling the model and training for around 300 epochs, I evaluated the models with the according performance metrics listed here. And to prevent overfitting, which is when the model learns the data a little bit too well and starts predicting the pattern of the data, leading to lower accuracy, I incorporated model callbacks to drop out of training after the learning curve plateaued. I constructed the sequential CNN model using stack generalization, and a stack dataset comprised the predictions from the individual transfer learning models. Then I fed that dataset through the stack model and evaluated the model with the same performance metrics shown in step 6. And finally, a conclusion was made. Okay, so elaborating on CNNs, a convolutional neural network, abbreviated as a CNN, is a deep learning algorithm which can take in an input image, assign learnable weights and biases to various aspects or objects in the image, and be able to differentiate one from the other. Convolutional neural networks have shown unsurpassed success in varying image classification tasks. How it works is that the image represented with a matrix of pixel values is passed through a series of convolutional linear pooling layers and fully connected layers, and then an output is generated. In the convolution layer, we take a filter and move this across the image from top left to bottom right. From each point of the image, a value is calculated based on the filter used in the convolution operation. And then after filters pass over the image, a feature map is generated for each filter, which is then passed through an activation function that decides whether a certain feature is present at a given location in the image. And after the nonlinear layer, which is abbreviated here as ReLU, is the pooling layer, which performs a downsampling operation. So the image volume is reduced, which reduces computational cost and training time. I used max pooling in the study because, which is the process where the kernel extracts the maximum value of the area it convolves. I chose this over other pooling methods such as average pooling because max pooling selects the brighter pixels from the image, which is useful for chest x-rays, especially due to the dark background, and preserves the sharp features of the image. Finally, there is the fully connected layer, which is a cheap way of learning nonlinear combinations of the high-level features from the outputs of the max pooling layer after flattening, and these layers are responsible for the classification into different classes. Okay, so now I'll talk about transfer learning and why I implemented it. So in transfer learning, we train a base network on a base data set and task, and then we repurpose the learned features or transfer them to a second target network to be trained on a target data set and task. So ImageNet is an image classification competition in which models are entered and tasked to classify millions of images into hundreds of classes or hundreds of categories. And the models trained on ImageNet have learned to detect generic features from photographs already. So transfer learning allows using these pre-trained weights for models that were trained on ImageNet or very large data sets as such, which would lead to higher accuracy when tasked with a smaller data set or when reused on a smaller data set. So this method is optimal for my small data set of chest x-rays. I chose 3 models to implement transfer learning on: Resonant 50, Inception Resonant version 2, and Exception, and I'll go into each of these transfer learning models later. Based on their individual performances in Pneumonia classification and other works, as well as their remarkable performances on ImageNet. You might remember that I froze the early layers in my procedure. This is because in the early layers of the CNN, the features are generic. The CNN can detect edges, curves, etc., while the later layers are dataset specific. So by freezing the early layers, we can accelerate training time. by skipping over the generic feature detection step and going right into the dataset specific feature detection. The three benefits of transfer learning are illustrated in Figure 4. With a higher start, the initial skill before refining the model on the source model is higher than it otherwise would be without transfer learning. Higher slope, the rate of improvement of skill during training of the source model is steeper than otherwise would be. And finally, higher asymptote. So the converged skill of the trained model is better than it otherwise would be. So it plateaus later, leading to higher accuracy when training. So here's my data set along with a few samples from each class. The data set is comprised of 5,857 X-ray images collected at Guangzhou Women and Children's Medical Center. I removed non-viral and bacterial pneumonia from the study as it's more pressing to classify between viral pneumonia and COVID-19. So now I'll explain why I used ensemble learning and what it is. So ensemble methods use multiple learning algorithms to obtain better predictive performance than that could be obtained from any of the constituent learning algorithms alone. So in this study, I implemented stack generalization, an ensemble algorithm where a new model is trained to combine the predictions from two or more models already trained on the data set. The level 0 models used in the study are Inception Resident version 2, and Resident 50. And a level 1 model, which is the Ensemble Meta Learner, is the sequential convolutional neural network. The ensembling technique I used is called stack generalization, and the reason why I chose this is because the meta model, the ensemble learning can be trained on the predictions of different base models. So this way I can reap the benefits of different CNN architectures instead of using the same constituent model architecture. Here I'll go into the model architectures chosen for this study. The ensemble constituent models chosen are Exception, Resident 50, and Inception version 2. In Exception, we can reduce computational complexity with depthwise separable convolutions. Every kernel is 2D and convoluted with one channel. It also outperforms Inception Net version 3, VGG Net, and Resident with the 94.5% accuracy in the ImageNet competition. Deep networks are hard to train because of the vanishing gradient problem, meaning that as the gradient is back propagated to earlier layers, repeated multiplication may make the gradient extremely small. So as a result, as the network goes deeper, its performance gets saturated and starts degrading rapidly. And Resonant allows us to train extremely deep neural networks with 150 plus layers successfully. What a breakthrough with skip-wise connections. And this model was a winner of ImageNet in 2015. Inception Resonant version 2 is like the intersection between Inception and Resonant. With its residual inception blocks, it can avoid the degradation problem as mentioned before, while being computationally efficient in training time. And it also had a 94.6% performance on ImageNet and outperformed Inception version 3 and Resonant 152. Okay, so here's my proposed stacked model. So first, I'll construct the individual models with pre-trained weights loaded from ImageNet, implementing transfer learning, with also fully connected dense layers for classification and fine-tuning. If we follow this diagram, here's the input, here's the individual transfer learning models constructed, and these the data passes through these fully connected classification layers. And the reason why you see softmax/sigmoid is because either activation function can be used in the study, but this depends on the number of classes classified. So sigmoid is used for binary classification, so normal versus pneumonia, and softmax is used for multi-class classification. So in this study, it's 3-category classification between pneumonia, normal, and COVID-19. The next step is to combine predictions into a stack data set, and the stack model is a sequential CNN again with 3 dense layers. And then here are the 3 dense layers. Again, softmax/sigmoid is the last activation function. And also the before passing through this layer, the predictions are flattened into a 12 by 1 vector. And then the output is either the binary classification or the 3-category classification. And if you're intimidated by like these fancy error functions here, they're basically like the difference between the actual output and the predicted output, and it's used to, and the error functions are used to measure the performance of a model as it trains. Okay, next slide. So here are my results. The stack model outperformed all constituent classifiers, exception resonant version 2 and resonant 50 in 3-class and binary classification, with an accuracy of 0.954 and 0.998 respectively. And here and to avoid the accuracy paradox in binary classification, which means that the model after training can boast a 95% accuracy, but that means that the other 5% was incorrectly classified, which is a pretty substantial amount. To counter this, multiple performance metrics besides accuracy were used to evaluate the individual models and the stacked model. The performance metrics used for binary classification are the Sorensen-Dice coefficient, ROC, AUC, and the accuracy. Accuracy, precision, and recall were used for 3-category classification. The Sorensen-Dice coefficient, shown in the slide as the F1 score, is the weighted average of precision and recall, and it's a popular metric for binary classification. The highest value is 1.0, indicating perfect precision in recall, and the lowest possible value is 0. ROC, AUC, also having a range of 0 and 1 inclusive, represents the degree of separability and measures the model's capability of distinguishing between classes by computing the area under the receiver operating characteristic or ROC curve. Precision quantifies the number of true positive class predictions, while recall is the percentage of true predictions classified. So accuracy is a fraction of, and also accuracy is a fraction of the correct predictions over the total number of predictions. And here you'll also see a grid, or 2 grids. These are confusion matrices. A confusion matrix is a table that is often used to describe the performance of a classification model or classifier on a set of test data for which the true values are known. So for listeners who are in AP Stats, you might have learned about the confusion matrix in when studying type 2 and type 1 errors. So the top left is a false negative. And this is a scan classified as normal, but the scan was pneumonia. Top right, true positive. This scan was correctly classified as pneumonia. And then the bottom left was a true negative, and this scan was correctly classified as normal. And then the bottom right represents a false positive. So a scan that was incorrectly classified as pneumonia, but the scan was actually a normal scan. And then here you'll see a ROC curve. So an ROC curve is a probability curve comparing false positive rate and true positive rate. Classifiers that give curves closer to the top left corner indicate a better performance, and the closer the curve comes to the 45-degree diagonal of the ROC space, which is represented by the 50-50 blue dashed line here. Oh, 1 second, sorry. 45 diagonal, yeah, the less accurate the test if it's closer to the blue dash line here. So you can see this model generated an ROC curve pretty close to the ideal point right about here. So the model performed fairly well. And then here is the precision recall curve. So the precision recall curve is constructed by calculating and plotting the precision against the recall for a single classifier at a variety of thresholds. And a curve close to the top right corner indicates high performance. So the top right coordinate is here. This is the ideal point, and here is the model generated precision recall curve. So as you can see, it's pretty close to the ideal point. So here's my conclusion. PneumoStack, this is what I call the stack model, performed significantly better than any of its constituent learners, as well as existing models used for pneumonia, binary and multi-class classification, shown in the chart. So this chart illustrates different studies of models proposed using the same data set. PneumoStack also performed better than individual models investigated in other studies, also just shown in the chart. And some limitations of the study include the training on a public data set, so the model is untrained on what may be characteristic features found in clinical data. To mitigate this, I may validate the model on clinical data in future studies if I get access to clinical data. To counter the class imbalances, if you remember from the dataset slide, the classes were pretty imbalanced in terms of scan number. I may use the synthetic minority oversampling technique. And I also may apply this model to other CNN tasks in bioinformatics to see if this superior performance over proposed methods in other studies projects onto other tasks. Challenges. There were many challenges. The most challenging part was to learn all the frameworks and languages needed for this project. This was my first research project involving machine learning and computer science, and I only learned Python this summer. So a substantial amount of the 500 hours spent on this project was reading literature, documentation, and tutorials. I frequently pulled all-nighters because I was so new to the field. And needed to learn advanced techniques to implement in this project. And also, since I was working with a novel ensemble, it was difficult to find literature and tutorials on stack generalization with a neural network as a meta learner with transferred learning models as base models. Because of this, I had no direct answer to my errors since I was proposing a novel method found on the internet. I needed to acquire relevant knowledge around the problem to conjure creative ways to solve the errors on my own. And also, other problems I encountered was the data set I used had many labels, and I needed a specific number of subclasses, 3 in my case. The CSV was not labeled in a clear way for stratification without modifying the data set, so I had to learn the library pandas for dataset preprocessing, cleaning the data with iteration, and I also had to construct a function to stratify the class labels. Additionally, I kept getting errors when implementing stack generalization. I frequently stared at one error for over 5 hours without knowing how to fix it, as the error wasn't on Stack Overflow, like I can't just search up how to fix it. So I had to read several cases of the error and irrelevant tasks to achieve an understanding of what might be wrong. And sift through my own code and experiment by adjusting hyperparameters, debugging by printing inputs and outputs, etc. And these errors occurred at the end of my code at the definition and training of the stack model after the training of the individual models. So I had to solve the error immediately or else I would disconnect from the server and retrain, which is a 5-hour process. And this process was very time consuming and demanding. So frequently I stayed up until 5 a.m. or later debugging because I didn't have the time to retrain all the models the next day. And my frustration can be illustrated with these memes. So what did I learn from overcoming these problems? Well, ultimately, I relied on my resilience and grit to overcome these problems after being faced with multiple errors that I stared at the day before for multiple hours. I woke up the next day, retrained, and worked on them again, even though I had no idea how to fix the error. I learned to have patience, to not give up, and to have faith that my hard work will be worth it in the end. And I now also know that the fundamentals of machine learning from my extensive literature and documentation review, despite starting this project with absolutely no machine learning knowledge. So this project was really, really rewarding. So here's my references, and that's it.
Wow. Somewhere about 10 minutes ago, you said something about if you're intimidated by this graph, and like I was intimidated by most of the graphs, but that was brilliant. I want to pause because I think Mr. Bink is on here, and I want somebody who might have science-related questions to ask, and then I'm going to comment a little bit on some leadership skills I definitely saw being developed. But does anybody have some science like questions related to the research? Yeah, I know some people are co-working as they're listening. Well, so Sonya, One thing that scientists and researchers often have to do is they have to get funding from capitalists who maybe don't speak their language. So I was wondering if you could take 30 seconds and say everything that you just said or what your project did in a way that somebody who has no computer science background or a health background could understand, because you need their money.
Okay, so my project, the aim of my project is to propose a novel approach to automated pneumonia and COVID-19 diagnosis. And why this is important is because it will confirmed by data studied by radiologists studying between or classifying between viral pneumonia and COVID-19. It's difficult to classify between these two diseases, and the precision is quite low, about 80%. So it's imperative to improve the diagnostic accuracy favorably with deep learning. So my approach would probably lead to automated diagnosis and widespread diagnosis of pneumonia and COVID-19 everywhere.
Awesome, thank you. Mr. Bink, I saw you put your camera on. Did you want to say something? Nope, okay. One further question. Well, actually two, and then we'll let you get back to where you need to go. Would you consider this to be more of a computer science project and research, or more health medical? Like what, or yes?
Well, I think there's like a lot of, there's opportunities for intersection between the two fields. So I would say both essentially, because it does use a computer science machine learning approach to solve a healthcare problem.
And if you were going to, I know you mentioned like that whole patience and resilience, but in terms of like how you obviously gained an awful lot of information about the computer background and science background and just research statistics that you needed to complete this. How have you evolved as a leader through this project?
Well, I did learn new depth of communication, which is very important for a leader to have. I took the first initiative to reach out to my mentor, to find a mentor, which was very intimidating at first. Like, why would an adult help a high school kid? Sorry, excuse me. So that was a daunting first step. And also the patience and grit and resilience that I mentioned before, just constantly just working at it until I get a result, and not giving up, which is, I think, a defining characteristic of a leader as well. Just working at it until something comes up and just not giving up before my desired result.
Sonya, thank you so much for presenting today. Thank you for presenting a few other places that we asked you to rather last minute hop on and talk about the wonderful things that our Stuart students are doing. Very grateful for your time for doing that. And don't be surprised when next year we tap you to speak again, perhaps at Lead Like a Girl. I'm going to be asking our juniors next year also to talk about some of the work that they've done in the future. Yes, Hannah, I agree. Mind-blowing. Completely. Thank you very much, Sonya. And I'm going to just pause for about 30 seconds. I think I saw Jaden hop on, but I also want to stop recording and then start recording again so we have it fresh. Sonya, I'm very impressed. Thank you so much for presenting today.
Thank you, everyone. Thank you. Have a good day, everyone.
I know you received a few weeks ago, but